Yes, sir.
All right, so let me share the screen and we'll start. All right, so can you see the screen?
Yes.
Okay, so last time we were talking about free body diagrams, right? Uh, we talked about some other things. We really revised Newton's laws of motion, and we did a problem. Is there anyone who has any question from the last lecture? Any questions from the previous lecture? All right, so if there is no question from the previous lecture, we'll continue with free body diagrams, right? Let's kind of start free body diagrams from the beginning. We know so far we have been dealing with multiple diagrams. I draw a body and then we draw forces on that body, something like this, as you can see over here. These type of diagrams are known as a free body diagram. These diagrams are simply a graphical representation that are used in physics and in other branches of science as well to help you to visualize the multiple forces or different physical quantities that are acting on a body, right? And some conditions are also given. A coordinate system is also defined, and then a free body diagram is completely described. So again, the purpose of a free body diagram is to help you to visualize physical quantities, right? I use the word physical quantities because I can say visualize forces. You can also visualize different moments that are acting on a system, which we'll learn in turning effect of forces, which would be the chapter will be coming to very soon, and help you understand different types of velocities and things that are there on the system. And then using using this visualization, we can perform the required calculations, right? And we can compute mechanics problems using these free body diagrams. So what are some of the important things that make up a free body diagram? That's a question we'll be asking now. What makes up a free body diagram? Does anyone have anything in mind? What would make up a free body diagram? What are some of the very essential things that we would need to draw a free body diagram? What information will be required?
Geometry.
Well, yes. You can definitely use the word geometry. Yes, you're absolutely right. Any other suggestion or any other?
Dots and
system.
lines. Dots and lines.
Dots and lines, yes, that's also part of geometry. Well, you guys are being very general, right? So let's break that down into physics. First of all, the lines idea that I think Taha or Muiz suggested is something we can represent with arrows. We can represent forces, velocities, and accelerations and these type of things, right? With arrows, or rotation of a body, or what torque that is acting on the system. You can represent those with arrows. With dots, you can essentially represent particles, right? And geometry is something we would be needing to define a coordinate system. So everything that you guys said so far all made sense, but we can talk about those things in terms of physics, right? All right. So for example, the first thing that you would need is to understand the problem, right? So first of all, you would be understanding a problem. What I mean by that is, for example, consider that you have a system which is like a car that moves on a road, right? So this is a car and it has to move on this road, right? So you will have this diagram where this is a car, suppose it's a car, uh, and it's moving on this road. So of course there would be some forces that would be acting on this car. Now you can see that for this type of a system, what coordinate system can I define? That's understanding the problem, right? So if you understand this problem, in this case, for example, a coordinate system which is like this and like this would be enough. Saying, suppose that this is x-axis, this is y-axis. You'd say that this is my coordinate system, where on the right-hand side, it's positive x. On the left-hand side, I'll say it's negative x. Downwards is negative y, upwards is positive y. Having this defined, I can now easily solve any problem that follows the same picture. What I mean by that is, for example, suppose that I have some other problem, a problem where you might have a surface that is inclined like this, and this is the level ground, and the surface is inclined at some angle theta. And on this surface, suppose you have a box. Now it's much more easier to define a rotated coordinate system. A coordinate system that is rotated as much as this surface is rotated from a level ground. Now, it will make sense very quickly to you in just a bit when I start drawing the forces. For example, let's come back to this one. The first one, let's call it first, let's call this second. In the first one, you can see that we would have forces that would be acting on the system. Suppose that there is a force that I apply some force on this car in this direction, and due to that, the car is moving in the forward direction. It would start accelerating. Now we are all aware of this thing, that if I apply a force, it will cause this object to accelerate. Once that happens, as soon as the car starts moving, some friction, dynamic friction would start developing. And let's call that small f. So here I have more or less defined some of the forces, where I can define more, saying that the weight of the car is this one downwards, which is mg, which is equal to w. And due to that, these tires which are touching the ground, there would be some overall normal reaction force from the ground on the car as well. So you can say more or less I have drawn all the forces that could be acting on a system of this car traveling on a road. You can clearly see all these arrows that I have drawn are completely agreeing with this coordinate system. So I can see that if the arrow is, for example, this n, if I look at this one, the arrow points directly upwards in the positive y direction. If I consider the weight of the car, it's the arrow that points directly downwards in the negative y direction. And what about capital F? It's an arrow that points directly to the right in the positive x direction, whereas small f points directly to the left in the negative x direction. So all of this, is that clear so far? Do you understand how this
Yes, I
simple
understand.
coordinate system relates to
Yes,
this?
sir.
All right.
Yes.
Okay. So now can you tell me, let's draw some of the forces on this second diagram. Let's avoid some cluttering. So I'll move this one over here and let's make it a bit bigger. All right. Now, let's draw some forces that could be acting on this diagram. Right? Suppose that I want the block to go upwards on the slope. So I'll push the block. which means I'm applying some force in this direction. So that then the block will go upwards. As soon as the block starts moving, there will be some friction that would develop, which would be in the opposite direction to that force. We know all of this now. The weight of the block would be directly downwards towards the center of the earth, which means that it would be like this. But the ground is also going to exert some force on the block, and that force will be, because the ground is exerting, so it would be like this, something like this, right? And let's call it a normal force. This is the force that the ground exerts on the block. Again, we have drawn more or less all of the forces that we can. Now the problem here is, how do I solve such a system? Think about this. You have one arrow that points directly downwards, but all the other arrows are pointing at some angle to these original X and Y axes. Does everyone agree with that, first of all?
Yes, sir.
Yes.
We use trigonometry.
Right. Yeah. So we can definitely use trigonometry, but the physics behind it is that we can say, oh my God, what do we do? But a solution to this thing is very simple. Just rotate your coordinate system. Simply rotate your coordinate system so that more of these arrows get along with each other. What I mean by that is, if I'm going to take this coordinate system, let's take the same coordinate system, and let's bring it over here as well. Now I'll tell you a key to solving all these problems, right? Can I rotate this with, okay, there is no tool that allows me to rotate this. Let's see, straighten. Never mind. I guess I'll have to do it myself. But what I'm going to do is I'm going to simply rotate this coordinate system. Let's rotate it in the anti-clockwise direction, which means in this direction. Now, simply doing this, understanding this thing is going to be a key to solving all of the problems in physics which have to do anything with mechanics, right? You can solve any of the problems because main idea is to understand the problem. And once you understand the problem, having a free body diagram and then defining a coordinate system is the most important part in solving physics problems. Once you get that, then everything becomes very simple, right? So in this case, as we now know that if I rotate this coordinate system, I can rotate it like this. Now this is my plus y, and this is my plus x, where this is my minus x, this is my minus y. Now compare your diagram with the coordinate system. More of the vectors are agreeing with the coordinate system, while only one vector, which is the weight vector, does not agree with the coordinate system. So if it's just one, we can apply trigonometry to it and deal with one of that instead of dealing with these three different vectors. Now, three of the vectors are completely agreeing with the coordinate system. And then we can say that, okay, all right, so this is n, this is f, this is, again, some other f force, and they all agree with the coordinate system. What about this w? We'll just resolve it into its components. By components, what I mean is, for example, all the components correspond to a particular coordinate system. For example, in this case, suppose if I had a force like this, then resolving this force, I would resolve it according to the coordinate system. So I'd resolve it in this direction, and I'd resolve it in this direction. In this case, W is pointing downwards, so that's my vector. I have to resolve this vector according to the coordinate system, which is this one. And so if I do that, I resolve it in this direction, for example, and in this direction. So what I mean by that is, once I start doing this on the diagram, I just mean that I need to resolve it in this one and in this one, where just if you do some of the math, then this angle is theta, and this becomes one of these components becomes mg sine of theta, while the other one becomes mg cos of theta, where mg is simply this w, right? Instead of writing mg, I should have written w at this point. So this is w. So we only had to resolve one vector into its components, and the rest of the three are agreeing with the coordinate system. That's the advantage of you defining a new coordinate system according to the problem. This was a very relatively simple problem. You can have problems where you have a lot of forces that are acting on the system. And in that case, it is more and more important to rotate your coordinate system rather than to resolve all of those forces into their components, right? It's easier to resolve one or two forces into its components while keeping the others as it is. So is this clear? Any questions from this?
Clear.
Sir, how did you
Could you explain
create,
it again?
from those forces into those diagrams which you created?
Okay, one question I think from Urva was if I can explain it again.
Sir, how did you create them?
And the other question is, how do I create them? Can you, are you Hassan? Right?
So there are two lessons.
Oh, there are two Hassans. Okay, all right. Okay, so the first question is, how do I create them? Can you be more specific? What do you mean? So I'll go down here and then we'll do. I think we'll do it again, right? Okay, so yeah, now ask your question. How do I? Your question was about diagrams. Can you please repeat it? Hassan, can you please repeat your question?
Sir, my question was, how did you manage to create a diagram of vectors from the original forces which you created?
Oh, okay. So you agree with this thing, at least you agree with this thing, that if I have this slope and it's at some angle theta, and there's a block on this slope, do you agree with all the forces that I drew on this block? So if I want to move the block upwards, I'll say I'll apply some capital F. That would create a frictional force that would be, you agree with this. You also agree with the fact that there would be some weight acting downwards and the normal force would be acting like this. You agree with all of this. Then defining a coordinate system, do you agree with this as well? A coordinate system, a more appropriate coordinate system for this thing is this one, where this is plus y. So it's kind of rotated at some angle theta, right? Plus x minus y. So if you consider original coordinate system, which was completely straight, where this was plus x plus y, this one is rotated by some angle theta, the left hand one. And it is rotated by the exact angle, which is this theta, the angle at which the slope is inclined on. So far, is all of this clear to you? Hassan?
Oh, sir, mic went off. Yeah, it's all clear now.
Okay, now because I did not really understand your question. What do you mean by how do I made a diagram of forces? Because that's these are the only things that I'm doing. Or are you asking how did I resolve the weight vector into its components?
So I had another.
How did you resolve the weight vectors? Yeah, that's the word I was looking for.
Okay, yeah. So I thought that could be your question. Okay, so I'll answer that. And the other Hassan was also asking something.
Yes, sir. So I wanted to ask, how does so you resolve them into
Two
two
components.
forces,
Yeah.
right? Yes, two
Yeah.
components. How did you resolve it into sine? How do we know that it's the horizontal force will be sine of theta
Let me
and the
do that.
vertical
Let me do that. I get you. So both of your questions are the same questions from same Hassans, different Hassans. All right. Okay. So do you agree with this thing that if I have a triangle like this, and if this is my 90-degree angle, and suppose the angle theta lies over here, then I can say that this is the base or the adjacent of the triangle. I can say that we say that this is the hypotenuse of the triangle, and this one is the opposite side to the angle. And then we can have a multiple expressions for sine, cos, and tan. We know we have sine theta then is opposite side over hypotenuse. We know cos theta is adjacent or base, let's say base over hypotenuse. And we don't need tan at this point, so I'm just going to ignore that. Now, if I look at all these vectors, so suppose these were my vectors, right? So this, according to this coordinate system, weight should be resolved into, this line is not straight. Let me just draw it again. It should be resolved into this one, and it should be resolved into this one. So I'm just going to draw it a bit, or let me use different colors. I apologize for the time delay. Just give me a second. Okay, so this is one, this should be one, and this should be the other one, right? According to this coordinate system. So this would make a triangle, really, right? If you really look at it, it makes a triangle. So for example, let's consider this triangle. This would be something like this small triangle. Now here we have this angle theta by geometry is this angle theta, and this one of the angles, this one is the right angle, right? And now if I use this thing, this is hypotenuse, this is opposite, and then this would be the base. Now what would be this line? It's base, right? And what do I have? The other one is, I know this one, which is W, which is weight. So I know hypotenuse, I know angle theta, I need base. What relates base and hypotenuse? Cos theta. So I use cos theta is equal to some base divided by hypotenuse, but that's W. So base becomes W cos theta, which means that this component, which I wrote as this thing, is W cos theta. Is that clear now?
Yes, sir.
Yes, sir.
Okay, amazing. Just give me 1 second, right? I'm getting an important text, and just let me get to that, and give me 1 second. Okay, anyways, all right. So is this clear for both of you? Hassan Naz and Hassan Sahal?
Sahal. Yes, sir.
Sorry for
Yes, sir.
Okay, is it clear for both, right? Okay, amazing. So in the same way, you can also write down the sine component. And I say that you should do it as an exercise so you can completely understand the idea. Because again, if you just listen to me and I say that, yes, I understand, and I do the other one for you as well, then by the end of the lecture, you might not remember exactly what happened. So do it as an exercise and try to figure out the other component as W sine theta as well. Okay, so Urva was asking to repeat it, right? Urva, coming to you, can you let me know from what part do you want me to repeat this entire coordinate system And how do I relate the coordinate system with these free body diagrams? Was that your question?
Yeah, I think so.
Okay, you think so. Interesting. All right. Okay, so I'll quickly repeat it. And let me use this. I'll just use yellow color pencil for fun. Okay. So the idea was to see how can I make a free body diagram. So I'm just quickly going to summarize things. And in this summary, I'm going to answer Urva's question as well. And it would be a summary for the rest of the class as well. All right, so the question was free body diagrams, right? Free body diagrams, and how do I relate these to the coordinate system? Suppose that, suppose that I have a block on a flat surface. I apply some force like this to the block starts moving to the right? And it also develops some friction to the left. Let's call it small f. The other this would be a pair of forces that would act on the system. The other pair of forces would be due to the fact that this object would have a weight. That's also a force. And because it's on the surface of the ground, there would be a normal force on this block as well. And let's call that capital N. So this is a free body diagram, right? So just drawing all the forces on what's happening to the block. All right. Now, a coordinate system, so once I drew all these forces, now if I want to do the math, I need to have a coordinate system. And this, by the way, for everyone, is the most important part of problem solving. I learned this at a very later stage in my life. So that's why if you are just starting physics O-level students, I would like you to understand this right now. Defining a coordinate system by understanding the problem is the most important part of solving problems in physics, right? So this simple statement is the key to science, or this should be your takeaway from today's lecture, right? Okay, so in this thing, I can clearly see that if I have a simple coordinate system, that would be enough, where I have upwards and downwards like this. So this is plus y, this is minus y, and then I have plus x like this and minus x like this. This is your simple traditional original coordinate system, Cartesian coordinate system also, sometimes it's called, and or a rectangular coordinate system also. So this would be enough, because you can clearly see that if I look at the force N, it is just in the positive y direction, right? According to this coordinate system. If I look at the force W, it is directly downwards in the negative y direction. If I look at this force capital F, it is to the right, which means it is directly in the positive x direction. And if I look at the small f, which is the friction, directly left, which means it's in the negative x direction. So they completely correspond to this particular coordinate system. That's the coordinate system for this problem. Having this with us, we can easily write down different equations. N minus W would be 0 if it's a stationary system. Generally, it's N minus W would be equal to MA, and the other equation would be F minus F would be equal to MA. These are the two set of equations. And if you solve these equations, these are also known as differential equations. You can write them as differential equations. And also these are called the equation of motion for the system. Having these two equations, now the problem is completely solved. Now, an examiner might ask you if this is the value of mass, if this is that, this is this, then calculate this. So that's simply putting in the values and then using these equations to solve the problem. But essentially, you have solved the problem. That's a simple free body diagram problem. Now, why is the choice of coordinate system important? That was my point. And that is, you will understand that if I choose another set of problem, where if I have an inclined plane and I have a block on this plane now, And suppose that this plane is inclined from the surface of the ground by some angle theta. Is that clear, by the way, Urva? Is this thing clear? The first thing.
Yes, it's clear.
Okay. So the second thing, I'll also give it a number, sec number 2, is now the whole purpose of doing the second thing is to completely make you familiar with why the choice of coordinate system is important. The forces on this system would be the weight acts directly downwards to the center of the earth. So I'll draw a straight downwards vector for weight. Because this block is sitting on this slope, it's sitting on some surface. The surface exerts a normal force on the block, which is drawn like this. Well and good. Suppose I want to push the block upwards the slope. I'm going to apply some force in this direction on the block. As soon as the block starts moving, friction starts developing in the opposite direction, and that's something like this. All right, have all the forces, well and good. Now, the problem here arises. If I look at this coordinate system, which was this one, and compare this with this coordinate system with this thing, what do you see? You see that, all right, well and good, W agrees with this coordinate system. It's downward, so it's in the minus y direction. But what about N, F, and small f? Do they agree with this coordinate system? No, they don't. By agreeing, what I mean is, are they pointing in the exact directions that we are seeing over here? No, they're not. N is pointing something like this, right? That's N. F is pointing something like this. That's F. Small f is pointing something like this. And so on, right? The only thing that agrees, that lies on this line, I'll draw it with this color, is W. That's agreeing, but that's only one. So we would have to resolve 3, N, small f, and capital F into components. But the easier thing to do is simply rotate the coordinate system. What I mean by that is, instead of having plus y here, I define a coordinate system where it follows this plus y with this N and plus x like this. Now let's check. Capital F lies on this. Small f also lies on this. N lies on this. The only thing that does not lie is one vector, and that's W, which points directly downwards. So now I only have to resolve one vector into its components instead of resolving 3 in this case. There were 3 vectors that I had to resolve: N, small f, capital F. Only W lied on the coordinate system. So Urva, is that clear?
Yes.
All right. So this thing should be clear. The choice of coordinate system and its relation to free body diagrams should be clear. And it's a very important point. In fact, this lecture is on free body diagrams is the most important lecture that you will ever have in your basic introductory physics classes, right? Because in this one, you always, some of the instructors, they don't go this far into the depth of these diagrams and their relation to coordinate systems. But because I have experienced that as well, so I wanted you all to know this thing from the beginning. And now, if you completely understand this, I would really urge all of you to go back and have a look at these. I'll share these notes with you. Go on internet, understand free body diagrams and their relation to coordinate systems. Because once you understand this, believe me, it's very easy to do physics, right? It's very simple to solve physics problems. All right, anyways, Okay, so Urva, do you also understand how would I resolve W into its components, or should I go over that again as well? I'll do it quickly if you want to.
I think I've understood that, I guess.
You guess. I think I'll go over that and we'll finish. We'll dedicate today's class entirely to free body diagrams, and the next class will start the next chapter because we have less than 2 minutes remaining anyways. So it would be pointless to start the new chapter in this time limit.
Excuse me, sir.
So yeah, is there any question from anyone?
Sir, can you please send a screenshot on the
Oh,
group
miss.
after resolving them?
After resolving, you want me to send a screenshot for I'll share these notes with you as soon as we're done
Yes.
with the class, right?
Mhm.
Right after we're done with the class, I'll share these notes in the group. Is that okay?
Yes.
Okay, great. So resolving these components, we have 1 minute remaining. Resolving these components, we just have to, we see that N is agreeing with the coordinate system, F is agreeing, small f is also agreeing. So we can write these things as N, F, F. These are completely okay. The only thing that's not okay is W. We have to resolve it. And resolving it according to this coordinate system, geometrically, this angle is theta as well, right? It's theta. Now, if I extend this line like this and extend this line like this, it forms a right angle triangle. So that's theta, this is 90 degrees, and this is my W, right? This line is W. So I need to find this line, this one. What is this? So I'll use these laws of triangle. Let me draw this triangle over here. This is 90, this is angle theta. So this is this, I can write it as cos theta